before you skip this video, this is actually something that I've recently encountered a lot of times through scrolling my social media. This is what I would call the oversaturation of AI. Of almost all things from studying to reading to all of this, there's always an AI investment, there's always an AI app. This feels like incredibly exhausting to see. Recently, I've been given a topic of AI used on the smart grid system. Honestly, I wanted to know further. I wanted to know how this differs from the usual LLMs that are promoted by these so-called creators. I mean, it's fun if it's just one, but honestly, there's multiple of them. And so, let's go. Let's discuss it. Good day to all of you. Today we're going to talk about something that most of us interacts with every single day without really thinking about it. From the moment you turned on the light this morning, charge your phone, or use anything that runs on electricity, you were depending on the power of the power grid. It is one of the most complex systems humanity has ever built, and for most of its history it has been managed the same way, reactively. Something breaks, someone fixes it. Demand spikes, operators respond. Works, but it is becoming increasingly clear that it is not built for that kind of future we're moving towards. Today, I want to talk to you how artificial intelligence is beginning to change that, and why the chemistry of energy storage makes the shift so important, and why the very technology solving one problem is quietly creating another one we also need to take very seriously. So, let's go. Now, we're going to proceed to move to date. Here's how we are going to move through today. We start with AI itself because I think it is worth being specific about what we actually mean when we say artificial intelligence, since the word gets used for a lot of very different things. From there, we move on to the power grid. What it is, how it works, traditionally, and what changes when you make it smart. Then we get into how both systems work together. And this is where the chemistry parts becomes directly relevant to what we are studying. And when we close to the impacts of all of this, both the benefits and the problem the technology generates for itself, that I think is worth sitting through. Let us get started. First, let's talk about what is AI. When most people hear the word artificial intelligence, they think something of like ChatGPT or maybe a self-driving car. But they are very different things. They're very different from each other. And that difference matters a lot when what we're talking about today. At its most basic level, artificial intelligence is a system that learns from data and uses what it has learned to make decisions or predictions. It is not magic. It is not one thing. It is a broad category of tools, each built for their own specific kind of problem. The keyword there is learn. Traditional software follows instruction a programmer wrote. AI systems develop their own internal rules based on patterns they find in the data. That distinction between following fixed instruction and learning from experience is what separates AI from the older automation system like the ones used in the planes like the autopilot system. And it is exactly what makes certain types of AI so well suited to managing something as complex and constantly changing as the power grid. So let's get into specific about the types of AI that are actually going to be relevant here. Because this is where a lot of presentations on this topic gets fake, and I want to be clear. The first type is a machine learning for load forecasting. This is the AI that predicts how much electricity is going to be needed and when. It looks at historical usages data, weather patterns, time of day of the week, and it builds a model out of that. That can predict demand with increasing accuracy over time. A study by Feng and Zhang at the University of Texas in Dallas found that a reinforcement learning system applied to short-term load forecasting improved prediction accuracy by around 50% compared to existing models. This is not a small improvement when you're talking about a system that serves millions of people. The second type is a neural network for anomaly detection. This is the AI that watches the grid continuously, every sensor, every line, every node, and flags anything that looks unusual before it becomes a failure. The third type is reinforcement learning. And this is the most important one for our purpose. Instead of being trained on a fixed data set, our reinforcement learning system learns by doing it. It interacts with the environment, makes decisions, gets rewarded for good outcomes, and gets penalized for bad ones. And over time, it gets better. It's the closest thing an AI has to genuine adaptive intelligence the human the humans have. And it is what makes the managing dynamic systems like grid possible. Now, all of these three are fundamentally different from older automation systems. A flight autopilot or an industrial control system like SCADA follows a fixed script. If this condition occurs, execute this response. Reliable but completely rigid. If something happens that was not anticipated in the programming, the system either fails or does nothing. Smart AI Grid does not have this limitation. It can respond to any situation it was programmed for because it has learned underlying patterns of the system that it is managing. Now, which AI is suitable for this? Now that we're dealing with the smart grid system, let us talk about which AI is suitable for this. If you had to choose one type of AI for smart grid management, the answer is deep reinforcement learning. And the reason comes down to the nature of the problem. The grid is never the same twice. Demand changes every hour, weather affects renewable output with unpredictability. A solar farm goes offline, a neighborhood all charges their electric vehicles at the same time. An industrial plant suddenly runs out of production. No 2 days are identical, and the number of variables the system has to account for simultaneously is enormous. Machine learning for load forecasting and neural networks for anomaly detection are both valuable tools, but they are best understood as supporting systems. They gather information and flag conditions. Reinforcement learning is what actually responds to that information and manages the grid in real time. A framework called AutoGrid AI, built on deep reinforcement learning, demonstrated significantly better performance in energy efficiency and operational resilience compared to traditional rule-based control systems, particularly when integrating renewable energy sources whose output is inherently variable. That is a proof of concept. Yet, that adaptability is not just useful, it is necessary. Now that we have a clear picture of what kind of AI we are actually talking about, let us turn to what is actually managing the power grid itself and what makes a smart grid fundamentally different from the one most of us grew up with. Now, let us first define what is a power grid. The traditional power grid has three main stages: generation, which is where electricity gets produced, typically at a large central power plant burning coal, gas, or nuclear fuel. Transmission, which is where electricity is moved over long distances through high voltages line. High voltage is used because it reduces energy loss as heat during transmission. And distribution, where voltage is stepped back down through a series of transformers until it reaches a level safe enough to enter your home or business. This is the system that has powered modern civilization for over a century. It is remarkable that it works as well as it does, but it was designed around a set of assumptions that are no longer true. It is assumed that energy would always come from small number of large, stable, centrally controlled sources. It assumed power would always flow in one direction. And it assumed that demand, while variable, would always be predictable enough to manage manually. None of these assumptions hold anymore, and that is a problem that smart grid is designed to solve. The grid is reactive. It needs to be predictive. The core limitation of traditional grid is captured in that phrase. It is reactive. When something goes wrong, operator responds. When demand spikes, they bring more generators online. When a line goes down, they reroute manually. This worked reasonably well when the system was simpler, but the energy landscape has changed dramatically. Solar panels on rooftops, wind farms in the ocean, EVs, and potentially returning power. Battery storage systems at neighborhood level. All of this introduce variability that the traditional reactive model cannot handle efficiently. A cloud passes over a solar field and output drops instantly. The grid needs to anticipate these changes before they happen, not respond to them after the fact that it has happened. That is to shift from reactive to predictive, and it is only possible with AI managing the real-time data flow at a scale and speed no human team could match. A 2025 study on AI-driven demand forecasting confirmed that renewable-dominated grids face constant supply and demand mismatches, and the traditional forecasting method simply cannot resolve. AI is not a luxury in this context. It is a requirement. So now that we know what AI is capable of and what a grid needs, let us get into how they actually work together. And this is where the chemistry becomes central to the conversation. A smart grid changes fundamental relationships between electricity, producers, and consumers. In the traditional grid, the relationship is simple. The plant makes power, you use it, end of story. In a smart grid, it is bidirectional. Electricity and information flows both ways. If you have a rooftop solar panels, you are not just a consumer. On a sunny afternoon when your panels are generating more than the household needs, that surplus of electricity flows back into the grid. During peak hours, when a local supplier meets demand, the grid draws from whatever it can, including consumers, have stored energy to give it back. Smart meters installed at homes and businesses makes this exchange possible by collecting real-time usage data continuously and feeding it back to the main management system. The AI that uses that data to balance supply and demand across thousands of simultaneous sources. Predict where shortfalls are developing, reroute power automatically, and optimize the charge and discharge cycles of batteries storing excess energy. All of this happens faster than any human operator could process the information, let alone act on it. Now, why does AI fit the grid? Now let's move on to why does AI fit the grid. The reason AI fits the system so naturally is scale and variability. A modern smart grid regenerates more sensor data per second than any human team could ever meaningfully process. Every smart meter, every battery, every solar panel, every wind turbine is constantly reporting its status. AI can monitor all of it simultaneously, identify where inefficiencies are forming, and respond before they become problems. The variability of renewable energy makes it especially critical. Solar generation depends entirely on cloud cover and the angle of the sun. Wind generation depends on wind speed, which can change dramatically within minutes. Neither is predictable, with the kind of precision a traditional grid management system requires. A 2025 study found that AI-driven forecasting systems significantly outperform traditional methods precisely because they could model these nonlinear, weather-dependent dynamics in real time. The grid generates enormous amounts of data. AI is the only tool capable of currently turning that data into decisions fast enough to keep the system stable. Now, with all that in place, it's finally discuss the chemistry behind energy storage. Now we get to the part that connects most of this directly to the chemistry. All of that variable renewable energy, all of the solar panels and wind farms, they do not generate power on a schedule that matches when people actually need it. The sun does not shine at peak exactly when the demand peaks. The wind does not blow on command. So the energy needs to be stored when it is available and released when it is needed. The primary technology for doing that at grid scale is the lithium-ion battery. And the reason it works comes down to electrochemistry. Inside the lithium-ion battery, there are three main components: an anode, a cathode, and then I think now we get to the part of this that connects most of this directly to chemistry. All of that variable renewable energy, all of those solar panels and wind farms, they do not generate power on a schedule that matches when people actually need it. The sun does not shine at peak exactly when the demand peaks. The wind does not blow on command. So the energy needs to be stored when it is available and released when it is needed. The primary technology for doing this at grid scale is a lithium-ion battery, and the reason it works comes down to the electrochemistry. Inside a lithium-ion battery, there are three main components: an anode, typically graphite; a cathode, typically lithium metal oxide; and an electrolyte, a liquid or gel that allows ions to move between them. When the battery charges, an external electrical current forces lithium ions to migrate to the cathode through the electrolyte to the anode. When they are stored, the battery discharges. Those ions moves back from the opposite direction, and the electrons that accompany that move and flow through an external circuit as an electrical current. That flow of electron is what we use as electricity. A 2024 study published in the Energy and Environmental Science confirmed that visibility and efficiency of this electrochemical process are what determines how reliable a battery performs over thousands of charges and discharges cycles. The AA managing the grid monitors all of these batteries in real time, using sensor data to keep the charge and discharge cycles within the optimal range, extending the battery's lifespan and preventing possible dangerous conditions like thermal runaway, which occurs when a battery generates more heat than it can safely dissipate and triggers an uncontrollable chemical chain reaction. Now, all of this follows a simple procedure called a redox reaction. This diagram illustrates the fundamental chemical process at work. Redox is short for reduction and oxidation. Oxidation is the loss of electrons. Reduction is the gain of electrons. They always happen together because electron lost by one species must be gained by another. In the context of lithium-ion battery, during the discharge, the anode material is oxidized. It releases electrons and lithium ions. The cathode material is reduced. It accepts those electrons and ions. During charging, the process reverses. The reason this matters for the grid is that the efficiency and reversibility of these reactions directly determine how much energy can be stored and retrieved over the battery's lifetime. Every time the reaction is pushed too hard, too fast, or outside its optimal temperature range, degradation accelerates. The AI system is essentially a precision manager for these chemical reactions, keeping them operating at their most stable and efficient point continuously. Now, there also exists other storage systems for energy. Lithium-ion batteries are the most widely discussed storage system technology, but there are actually more than one deployed at grid scale. Pumped hydroelectric storage is actually the largest form of grid-scale energy storage in the world today. It works on a straightforward physical principle. When there is excess energy available, water is pumped from a lower reservoir to a higher one. That water holds the gravitational potential energy. When electricity is needed, the water is released back down through the turbines, converting that potential energy back into electricity. It is essentially a giant rechargeable battery using water and gravity instead of chemistry. Flywheel storage works differently. Energy is used to spin a large mass at a very high speed. That traditional kinetic energy is stored within it until it is needed, at which point the spinning mass drives a generator. Flywheels respond extremely quickly, which makes them useful for short-term grid stabilization. Each of these storage systems has its own physical and chemical traits. Pumped hydro requires specific geography. Flywheels are fast but limited in capacity. Lithium-ion is versatile but expensive and chemically complex. The AI coordinating a smart grid manages all of these systems simultaneously, directing where energy goes and when, based on a continuous real-time assessment of supply and demand, storage, state across the entire network. Now, let's move on to the heat problem. Now we come to the part of the presentation that I think deserves the most honest discussion. The AI system doing all of this work, the load forecasting, the anomaly detection, and the real-time decision making, they do not run on air. They run on a massive computational infrastructure housed in data centers consuming enormous amount of electricity. And that electricity, like all energy, does not disappear. When it is used, a portion of it becomes useful computation, and the rest is released as heat. This is not a design flaw, it is thermodynamics. The second law of thermodynamics tells us that no energy conversion is perfectly efficient. There is always waste heat. At the scale that the modern AI infrastructure operates, that waste heat adds up very fast. A 2025 study projected that global data center electricity demand could grow from an approximately 415 terawatt hours in 2024 to nearly 945 terawatt hour per hours by 2030, with AI workloads driving disproportionate share of that growth. To put that in context, 945 terawatt hours is more than the entire annual electricity consumption of many individual counties. Cooling those facilities accounts for 30 to 40% of their total energy use. So the system designed to make our energy grid more efficient has its own significant and growing energy footprint. That tension is real in this sport sitting with before we talk and what about it is being done. Now, we're on the final section now. The impacts of this technology, which includes both water costs, cooling, AI infrastructure, and the solution that the field is actively developing. But why water? The primary tool for managing the heat generated by data center is water. And the reason comes down to a specific chemical property called a specific heat capacity. Specific heat capacity is the amount of energy required to raise a temperature of 1 gram of substance by 1 degree Celsius. For water, that value is 4.18 joules per gram per degree Celsius. That is exceptionally high compared to most common substances. Air, for comparison, has a specific heat of about 1 joule per gram per degree. This means that water can absorb roughly 4 times more thermal energy than air for the same mass before its temperature rises by the same amount. In practical terms, this makes water extraordinarily effective at carrying heat away from computing hardware. In the data center cooling system, water circulates through heat exchangers in close contacts with servers, absorbing thermal energy they generate, and carries it away to be dissipated through cooling towers or other systems. The thermochemistry here is straightforward. The water absorbs heat energy, its temperature rises, that energy is then transferred to the surrounding environment. Water is also abundant. Relatively inexpensive, non-toxic, and easy to work with at scale. All of these properties make it difficult choice for a large-scale thermal management. But as we're about to see, abundant does not mean unlimited. The cost. 1 year, 1 century. That is the estimated volume of water consumed by the United States data center through cooling alone in 2023. According to the report from the Lawrence Berkeley National Laboratory, and the projection suggests that figure could double or even quadruple by 2028 as AI workloads continues to grow. To make that number more concrete, researchers found that training a single AI model, specifically GPT-3 in Microsoft's data center, directly evaporated about 700,000 liters of fresh water. One model, one training run. This is not a hypothetical future concern. It is already happening at scale, and it raises real questions about sustainability, particularly in regions where fresh water is already scarce. Now, I want to be clear that this is not a reason to abandon the technology. It is a reason to develop it carefully and invest seriously in reducing what it costs. The field is actively working on this. Immersion cooling, where hardware is submerged directly in thermally conductive, electricity insulating liquid, significantly reducing water consumption compared to the conventional air and water-based cooling system. Waste heat recovery system capture thermal energy generated by data centers and redirects it for use in building and heating or industrial process, improving overall energy efficiency. The same 2025 study that projected the growth in data centers' energy demand also found that advanced cooling techniques can actually reduce cooling energy by up to 50%, and situating data centers in a water-secure regions powered by renewable energy can cut combined environmental footprint by nearly half. The problem is real. The solutions are in development, and then understanding the chemistry behind both is what allows us to evaluate them honestly. Now, to bring everything all together, AI-powered smart grid management represents a genuine shift in how we think about energy distribution. If it moves us from a system that reacts to one that anticipates, it allows renewable energy sources to be integrated at a scale that was previously impossible. It uses electrochemistry to store energy, thermal chemistry to understand its costs, and machine learning to manage all of it in real time. But it also requires infrastructure that consumes significant resources on its own. The chemistry that powers AI and the chemistry that AI helps manage are more connected than they first appear, and understanding both questions and both sides of these equations is what separates using this technology well from simply using it. So that would be all from me. Thank you very much.